Okay, hi everybody, thank you so much for coming. So I'm very happy to introduce Professor Jens Kober, who is an associate professor at TU Delft. He's a very well-respected researcher, professor in both machine learning and robotics, and particularly on how robots and humans robots can learn interactively from humans, which is what he was awarded an ERC starting grant for, and which is the topic of his talk today. So I'm really looking forward to it myself. Hope you learned something from today. And Jens, thanks so much for coming, and over to you.
Thanks a lot for the very kind introduction and having me. So indeed, I'm today mainly going to talk about the results we had from this big project. We're still working on it, but I'm a bit more towards actually applying it to real-world settings. Before I actually dive into the details of the methods, I very briefly wanted to start with an introduction. It's not going to be terribly scientific. I'm not an expert on that, but like many people, I at least take inspiration from human learning. And I believe there's lots of parallels between how humans learn and how robots potentially can learn. I guess all of you are familiar with imitation learning and reinforcement learning. Imitation learning being the idea that a robot learns from demonstration and then tries to mimic that, which works fairly well for simple tasks, and for more complex tasks like humans, robots also need to practice, which you call reinforcement learning. And to actually make those work nicely, there's many ideas you can take from human learning. So for example, also for human kids, it takes quite long until they can do this fairly simple task of goal-oriented grasping. But once they've learned that, they're pretty good at generalizing that, applying it to new tasks, new different settings. And then you can also transfer that to related but novel tasks, like that you first need to flip out something before you can grasp the book here. So effectively what you do is build up a skill library and then try to figure out if you can actually transfer one of the previous skills you've learned to something new. And there's quite a lot of approaches in robot learning that do very similar things. Other ideas are having a notion of intuitive physics, so you know that the apple is going to drop down and you can reason about it and then make use of that to actually inform the movement you're going to do. And if you have this kind of at least a rough simulation, then you can also do mental rehearsal, which is kind of similar to sim-to-real approaches. And then what I'm really interested in, like Ed was just saying, is this idea of learning in interaction with teachers. So here's a couple of examples from sports where you probably would not be totally on your own trying to learn a new sport, but rather you're going to have interactions with a coach who is going to tell you, try this, focus on that, practice that, you're doing well, this needs improvement, and so forth. And similar for human kids when they interact with their parents and other caregivers. So this talk is really going to be about teaching through interactions, to have some kind of continued student-teacher interaction, which could be additional demonstrations, some other kind of feedback, not continuously, but once in a while, so intermittently. When we started working on that about 10 years ago or so, there wasn't much out there, but that's now actually coming up more and more in robot learning, where people realize that really you can speed up things if you pick the human's brain. So the benefits of this idea, hopefully I'll be able to convince you by the end of this talk, are that you really can drastically speed up the learning process, which enables the robot then to hopefully learn more complex tasks. And hopefully that's also somewhat intuitive for the human teacher. I have some evidence for that, because we are very good at this kind of teaching, not only with fellow humans, but other agents as well, like these animals here, for example. The remainder of my talk is going to be structured in two parts. First, I'm going to talk about one approach where we use this kind of human-in-the-loop learning for reinforcement learning. And then the second half of the talk is going to be about interactive imitation learning. Before I dive into the idea of interactive reinforcement learning, I wanted to very briefly show you an example of some of my really early work. That's my cousin's daughter. She was about 10 back then. Task is ball in a cup. Took her 35 times to catch the ball, and that's the reward function there, actually. Okay, so we actually showed her how to do that first, similar here for the robot. One initial demonstration. If you just play that back, it kind of works, but it's not really accurate enough. And then after some trial and error, it's a lot closer. After some 45 trials, it sometimes goes in, usually bounces off, and after 100 trials, it has nicely converged. And if I give the toy to one of you, usually around 20 or so trials until you get it in the first time. So same order of magnitude, but then the question is, can't we do better? Yeah, and that's where the interactive learning comes in. The general framework is going to look something like this, which is very similar to what you would have in a typical reinforcement learning loop or some kind of a control loop. So you have the environment and your state, robot position, object positions, and so forth. And then the agent is supposed to learn a policy, which maps the current state to the action it's supposed to do. And typically, it's going to be parameterized in some form. In the rest of the talk, I'm going to show you quite a few different variants ranging from Gaussian processes to neural networks. Robot executes an action, and then you have this typical loop. Now what we have additionally is literally a human teacher in the center, in the loop. And we are going to assume that the teacher is going to observe the state the robot and the environment are in, and also that they can observe the actions that the robot is doing. And then the task of the human teacher is to once in a while provide some kind of feedback, which is going to help the robot learn the policy. The feedback could be some quite different things. On the one end of the spectrum, you could say, let's just do binary feedback, 1 for success, 0 for failure, so evaluative feedback. That's probably going to be fairly easy for the human teacher. However, like in a sparse reward setting for reinforcement learning, that's not going to be very informative for the robot agent. And on the other end of the spectrum, you could say the task of the human teacher is to provide the perfect action for a certain state, which then makes it somewhat close to more classical imitation learning. That makes the life of the robot very easy, but then is a lot more demanding for the human teacher. What we figured out works fairly well is what I have on the slide here, actually using corrections. So correction on the action, which is something like move more to the right, move more to the left, move faster, move slower. So a form of a relative offset, not giving you the correct action, but a direction in which you should change the action. So it's kind of a gradient. And that's, at least for the tasks we considered, that are movements on the order of a couple of seconds to maybe a minute. That's kind of the sweet spot. So how that looks like is something like this. Some of the things I'm going to show you in the remainder of the talk are actually based on this algorithm that my former postdoc came up with, which is, has a very nice acronym COACH. So the goal is to have the robot drive on the right side of the road from top to bottom. Sorry, I'm based in continental Europe. And then it has an initial policy, the red line, which does something kind of in the right direction, but is somewhat random. And then what you see on the slide now is the intermittent corrections of the human teacher, that in this case literally is saying more to the left, more to the right, in order to fix up the policy. What we also figured out is that it's very important that the human teacher gets direct feedback from the robot, so that the robot directly reacts to the correction you give. So if you press the button for move more to the left, that the robot actually executes that action as well. Otherwise, if you're kind of trying to blindly correct things and the robot only applies the corrections after an episode, for instance, that makes it very hard for the human teacher. So you start with one episode, you provide a few corrections, and then hopefully in the next iteration the robot has learned from that, and you need less corrections, and by the end the robot can do it autonomously, at least if you're in the same setting. Okay, so this is more or less in an imitation learning setting, and now we could say, let's combine that together with reinforcement learning, so effectively replace the first part where I was showing you the kinesthetic demonstration in the ball and the cap task. Actually, Katharina, my colleague back then, needed to practice quite a lot until she actually managed to do a good demonstration with this interactive approach. So you start out with providing interactive corrections to get the robot in the right region, and then you use policy search or reinforcement learning to fine-tune that. That works, but effectively you don't gain much. Gets a lot? Yeah. So if you use these kind of interactive correction things, you don't actually need an initial policy. So how it works in practice is that if you start from scratch, then effectively you're teleoperating the robot in the beginning and it slowly learns from that. If you have the possibility to get an initial policy from a kinesthetic demonstration, and you just want to fine-tune that, that works probably even better. So we didn't want to do it sequentially, but actually combine it in one framework. So something that looks something like this, where we now actually model the teacher interaction and feedback as a form of exploration. I suppose most of you are familiar with reinforcement learning, where you actually also need exploration, so the robot trying out different strategies in order to figure out what works and what doesn't. In the vanilla reinforcement learning setting, that would be some random perturbations. But if we actually consider the teacher interactions as a form of exploration, we can use fairly standard policy search methods in combination with human feedback. So that looks something like this. That's a very standard policy search setup. So you have this loop here where you start with your current policy, the best guess you have, and then you do a few iterations where you have the exploration here. So you, oops, no. So there you have the exploration here, and you try out different variants of the policy. You evaluate them here, you see what works and what doesn't, and so you calculate the return in this case, and based on that you update the policy parameters, and then you rinse and repeat. So that's standard policy search. Now if we make it interactive, we have this switch in there. If we have human guidance, it effectively uses the coach approach, and the robot reacts to your corrections. And then we store the outcome of that in the same way and evaluate the cost. While you have the hard switch here between human guidance true or autonomous exploration is that it tends to get very confusing if you start correcting and the robot tries some random stuff on its own in parallel. So that's why we only rely on the human feedback and interactions once you actually start interacting with it. And in that way, you can actually use the human guidance exactly the same way you would use a different form of exploration. That obviously comes with one downside in the sense that both evaluation and the update are based on the robot reward function. So that means that the goals of the robot and the human teacher actually need to be aligned in some form. If the human teacher tries to teach something different from what the robot wants to achieve, then the worst that can happen is that it's going to get a very bad evaluation there and it's totally going to ignore what the human teacher is doing. We've also tried making that a bit more flexible by actually doing some inverse reinforcement learning additionally to that works for simple tasks, but is not that stable for more complex things, unfortunately. So now here, again, ball in a cup. Now we can actually start from scratch without an initial demonstration. What you don't see is Carlos, my former postdoc, providing corrections with a keyboard in front of the robot. Like here again, move left, right, slower, faster, these kind of things. And then it takes some 20 trials or so until the robot can catch the ball in the cup. And here once more in slow-mo. So actually, we're quite a lot faster now. Here's a little plot on how that looks like. Here you have the number of rollouts, the number of times the robot tried. And then to make things confusing, I'm plotting here the costs and not the rewards, so lower is better. In red, we see reinforcement learning on its own. And note here in this plot, this is the setting I had in the first video, so there's where we start from an initial demonstration. And then it takes some 40, 50 trials or so until it works with reinforcement learning. In green, we see using only interactive imitation learning, so it's a lot faster. But then also you see here at the end, it levels off because we start to hit kind of the limits of how detailed the feedback of the human teacher can be and reaction times and these kind of things. And then in blue, that's the combined interactive learning with reinforcement learning. So you can see we're as fast as using imitation learning, but then we actually managed to get a better result in the end. And then if we look at the plot for what I just showed you in the video, where we start from scratch without an initial policy, for the interactive approaches, that doesn't change much, but for pure reinforcement learning, that takes at least 200 trials or so until we can learn it. So this very nicely illustrates how this idea of interactive learning plays to the strength of both the robot and the human. The human teacher is very good at getting the robot in the right ballpark, so getting it roughly to the correct policy. And the robot is very good at doing things reproducibly and fine-tuning the policy. So that's it on interactive reinforcement learning. And in the rest of the talk, I'm going to talk about interactive imitation learning. So that means the robot does not have its own reward function it tries to optimize for. Rather, whatever the teacher shows, that's by definition the correct thing to do. Yeah, so this is a slightly different setting. The first examples I showed you were really on the level of the movement itself. The next approach I'm going to talk about is on a slightly higher level, where we were actually interested in sequences of tasks and figuring out which reference frames the robot is using, which will then hopefully enable generalization. So the typical example is, okay, you want to figure out if you're supposed to move relative to the MAC or world coordinates. Probably the correct thing to do is move relative to the MAC so you can grasp it wherever it is on the table. And here we make it even more complex by additionally having this coaster here, which has its own reference frame. Now, if the coaster and the MAG are always together when you provide the demonstrations, then you can't really figure out just based on the demonstration data, based on the statistics therein, if the correct reference frame is the coaster or the cup. You could put in some prior knowledge on, okay, the object I'm touching, that's the correct one or something like that, but then you would need to come up with a whole lot of heuristics to make it work. Yeah. The other interesting thing is, as long as the cup and the coaster are together, it actually doesn't really matter. So no matter if you move relative to the coaster or the cup, the movement is going to be the same, and they are actually equivalent. When it becomes interesting is when you start to separate the two, like you see in the thought bubbles there. So then you have the ambiguity, and the robot really needs to decide what to do. And that's exactly what we try to do here, to not bother the human teacher as long as it doesn't matter, but only actually actively query the human teacher once you have this ambiguity that needs to be resolved. So that looks something like this. We already taught the robot on how to pick up the cucumber and put it into a crate. And it can generalize that to different initial positions of the cucumber. But the crate with the cucumbers always was here at the bottom. And now we flipped the position of the two crates. And exactly like I had on the previous slide, now the robot needs to decide to move, whether it should move relative to the world coordinates or relative to the crate. What it's going to do now is going to start with the movement autonomously and move as far as it can. And then once it starts hitting this ambiguity, it's going to stop and implicitly request feedback from the human teacher. And then Giovanni is going to just give it a little push in the right direction, which allows it to figure out, okay, in this situation, that's the correct reference frame. And from then onwards, it hopefully can do it autonomously. We also ran a user study with that here in a slightly different setting. The task is to stack these boxes of tea in a certain order, kind of what should be on top of which is defined. And then we compared kinesthetic demonstrations, where you actually, as a teacher, need to make sure that you provide kind of all the different configurations you need that provides sufficient statistics to disambiguate the different possibilities. And quite often you'll actually figure out, okay, I forgot one configuration, and you kind of implicitly get this interactive approach already, that you start providing a bunch of demonstrations, robot learns, you test it, doesn't work, okay, you need to go back, provide more demonstrations. Then we compare that to our interactive approach, which is called LIRA, learning interactively to resolve ambiguities, where we start with a single kinesthetic demonstration. And then the robot, again, tries to do it as autonomously as possible. And when it's unsure, it's going to request user feedback. And it just takes a couple of iterations until it can learn the task. And we actually also wanted to know how people rate these different approaches. So Kate here is the kinesthetic teach-in, pure imitation learning approach, and Lira is the interactive imitation learning approach. It's NASA TLX score, and lower is better. And there you can see that the participants very consistently rated the interactive approach better. And if we talk to them, they really preferred A, because it's quicker to teach, and B, because the robot actually does quite a lot of thinking for them and guides them in the process, and it just makes it a lot more intuitive to teach. So that was more on the level of the sequence and figuring out some higher level parameters. Now I'm going to go back to the example I showed you in the very beginning on having a little robot drive. But now we actually want to move to having images as inputs. It's going to be very standard and classical, using some kind of an autoencoder structure to get a compact latent representation on top of which we can then learn the actual policy. So you could say, let's pre-train that. You collect a number of demonstrations or some other data. You pre-train this latent representation using the reconstruction loss. And then once that's trained, we actually start training a policy. And then either you freeze the encoder or you continue fine-tuning that together with the policy. That obviously works. But it requires that you first collect some data, and that the data you collect is actually representative of the task you want to do in the end. And also here, our question was, can't we do that nicer? Can't we actually do that together? So something like this, where we have the reconstruction loss here as an auxiliary cost function, and the main criterion really is learning the policy. Why this works here is, like I was answering to your question, is that effectively, if you start from scratch, you need to teleoperate the robot anyhow. So by the time you have collected enough data that it can learn some kind of meaningful policy, it also has collected enough data that you can train the reconstruction with the decoder. So in terms of kind of the amount of time you need for training, it's equally quick for the interactive part, and you totally don't need to do the first step of collecting the data, and the final results in terms of performance are actually better. So here is a corresponding video having the Stucky bot drive on the right side of the road. On top, that's the crappy camera image we get. On the bottom, that's the reconstruction. Compared to pure autoencoders, the reconstruction is actually pretty bad, but we don't really care about it, as long as it captures all the details we need to enable the robot to correctly perform the task. So it's sufficient for the policy, like whatever the road boundaries and lane markings, that's good enough. And now you can actually see how that looks like here. We provide feedback using the arrow keys on the keyboard. If you want to see how well it does, you take off your hand, see if it does well enough. If yes, you're happy and you're done. If not, you just continue providing a few more corrections. And it takes some 10 minutes or so for training the tasks. From scratch, no simulation, no pre-training whatsoever. There, what we did was just use a single image, and then that's sufficient for steering if you want to drive at a constant velocity. For more complex tasks, you could stack some images if you want to reconstruct velocities as well, or some other tasks might require other forms of memory. And then again, very classically, you put in some recurrent unit, in this case an LSTM, in order to actually have the latent representation with some memory. And then the other thing that changes here is that now the reconstruction is not the same image, but the image of the next time step to actually capture the dynamics. Here's a very simple setting of an inverted pendulum swing up. We can see the network input and then some predictions, and then again takes some couple of minutes to learn it. And I can work, I can do the task purely based on visual input, not using the encoders that we have in that system as well. So it's a weight on a disk which is physically equivalent to a pendulum. And then here the other example, we have a different form of memory. What the robot sees is the camera input on the top. However, what it can really see is only this white part here, and then you see in the middle there the cropped part. So it actually needs to memorize where the fake oranges are in order to be able to touch them, whatever, half a second later. And on the bottom, again, you have the reconstruction. So as you could see in the video, already after 5 minutes, it does pretty well. And then after 15 minutes or so, it has nicely converged. And there, again, you could see the keyword we use for input. And then what's really cool is if we have already a decent representation and we want to generalize to a new task, but related task. So in this case, it's avoid those pairs. You can continue training to adapt it to this new task. So you provide a few more corrections. You could see it in with the keyboard there. And then literally after 3 minutes, it already does a pretty good job at that. So, so far the corrections were actually in action space. However, that's obviously very direct. But if you look at this kind of robot here, it starts to get high dimensional. And as you can imagine, doing things in joint space, if you're not a robotics expert, or even if you are a robotics expert, gets to be quite non-intuitive. So rather than doing that, you might want to do it in state space or end effector space. For that, you would need some inverse model that maps from the end effector position to the joint configuration. For robot manipulator, you have your built-in inverse kinematics, so that's all nice and good. But for some other tasks, you might actually not have that. So what we wanted to look into is actually learning this inverse model and the policy at the same time. It looks something like this. So the task here is to trace a shape on the whiteboard using a laser pointer that's attached to the end of the robot. And then the corrections we want to do are really in the space of the whiteboard. So you want to move around on the two-dimensional space of the whiteboard. Yeah, you could do some calibration and figure it out. But here, actually, it's learning both the inverse model and the policy at the same time. And then, again, within less than 10 minutes, it can do the task. And yeah, as you can see, it was a publication for Coral, so your Coral, actually. And so here's the final result. Yeah, the tasks I've shown you so far were essentially kinematic trajectories in free air, but I believe things become a lot more interesting if you're actually in contact with the environment. So that's what the next bit is going to be about. The first one I want to talk about is an approach we came up with for learning both trajectories and then forces, or in this case actually an impedance controller, so the stiffness and damping. If you do these kind of tasks where you have interactions with the environment, it gets a bit tricky depending on what you do. If you're using kinesthetic demonstrations, then touching the robot screws up some of the sensor readings. If you can get away with it, kinesthetic demonstrations are actually the most intuitive for users in our experience. But then in this case, we need to switch to a different modality of feedback after that initial step. So what we do here is we provide one initial kinesthetic demonstration that's mainly used for learning the trajectory, which in this case is represented by a Gaussian process model. And then we use a space mouse or a 6D mouse to provide corrections that are going to be used to adapt both the trajectory and the stiffness. Very classical whiteboard wiping task. Here's the initial demonstration. If you just play that back, I didn't know that it's supposed to apply a force, or more precisely to have an attractor that is actually below the surface of the whiteboard. So what Anna is doing now is pushing down on the space mouse in order to provide a correction when it's in contact with the whiteboard. That's adapting both the trajectory, and what you see on top is also the stiffness. With just a single demonstration, you can actually correct that, and it does it nicely. It looks something like this. So the table is coming out of the screen, and that's when we are in contact with the whiteboard. In red is the original trajectory, in black is the adapted final trajectory. The background colors are the forces it applies, and then what you also see is this kind of a vector field, which is represented using a Gaussian process. How this representation we came up with works is that it's trying to minimize the uncertainty. For a Gaussian process, the typical uncertainty representation tells you if you have data in a certain region or not. So what it does, and what the arrows represents, it's trying to pull the robot back into a region where it's more certain. So then it nicely kind of always converges back to the area where we have demonstrations. Here's another example, different kind of interaction that was from a project together with a Dutch supermarket chain, where they were interested in seeing how far you could get robots in a retail setting, and then for restocking, they told us really you need to get it below 5 seconds, so that makes any kind of sense. Also here we started with initial kinesthetic demonstration, and now we're using these interactive corrections to both correct the movement or the trajectory, but then also to tell it in which parts of the movement it can speed up. So initially it was some 20 seconds or so, and now slowly we are pushing it towards getting to 5 seconds. So now that's in real time, the movement. Maybe one additional interesting tidbit is, not sure if you've worked with a Franca Emica robot. The gripper is kind of crappy, and the timing of the gripper for us was plus minus half a second. So actually need to teach a trajectory that is robust to that imprecision in the robot itself. Here we also did a user study with that. That was then a simplified setting. And here you can also see how you can actually extend it if you have some form of perception to be able to deal with moving objects. And what you could see here in this final bit is if you start moving too far away from what it has seen, then it becomes very uncertain, but the gradient of the uncertainty also becomes flat. So it just doesn't do anything and is safe in that sense. For the user study, we really thought that people would very much prefer being able to teach the trajectory corrections and the speed of the movement separately, because we thought that would minimize the mental load. Turns out we were maybe 50% correct, so there were really a nice bimodal distribution of participants. Some participants very strongly preferred teaching it in the way with the separate kind of two input modalities, while others really strongly preferred teaching it all together and then just using corrections to kind of push it forward in order to speed it up. Yeah, so, and the feedback we got was doing it separately really allows you to focus on one of the things, while the other people said, yeah, it's too demanding to think about which of the modalities I want to use now. So, yeah. Unfortunately, it seems that there's no one-size-fits-all in terms of how users like to teach robots. And also, it differs quite a lot between different user groups. People that are avid video gamers, they're very good at these kind of things, and they actually have quite different preferences than people that don't. Or here's one other approach, extending it to bimanual settings. What you also hear, one of the big questions was how do we actually make it feasible for human teachers? And what we came up with is teaching the two arms separately and then using corrections both for the trajectories and for figuring out how they should be synchronized. And then you can do these kind of tasks like moving crates, but also handover tasks and so forth. I already talked quite a lot about different ways of providing feedback and the challenges you have with defining good interfaces and making that feasible for human teachers. And it gets a lot worse than that. So here's a schematic overview of some of the things you could do. So you, here on the bottom, you could have a human-gated, human-driven feedback where you assume that the teacher is going to jump in and then either provide some evaluative feedback and tell the robot what it's doing good or bad, so provide some kind of a rating, or you could have the user provide corrections or absolute actions, but you could also have the robot being more active, so kind of an active learning approach where it's actively requesting input or feedback from the human teacher. And also there you could distinguish between different types of uncertainty. Maybe it's epistemic and you just don't have any data for a certain setting yet, and then you ask the user to provide more data. Or if it's aleatoric, then maybe you have provided contradictory demonstrations and it needs to figure out what the correct thing to do is. And then also for those, you could have different instantiations of exactly how the feedback looks like. So what we tried in this paper is come up with a way that allow us to combine all these different types of interactions in one framework. From a learning point of view, I think we managed quite well, and you can do that, and it actually works quite well. You can do fun stuff like this very dynamic kind of air hockey-like task of catching the little card, which is actually too fast for teleoperating the robot. It works very well if you have a simulated teacher or if you're the first author of the paper and you've practiced with the robot and the framework quite a lot. However, if you ask people that haven't seen the framework before, then it very quickly becomes overwhelming. So yeah, there's still quite a lot to do in figuring out how that interaction should look like, not only to enable the robots to learn quickly, but also to make it user-friendly. The final thing I wanted to show you is from a few competitions we've participated in. Actually, the team won a challenge at IROS a couple of weeks ago. Again, here we're going to start with an initial kinesthetic demonstration. And then we're refining the subparts of this more complex task using corrections, but then also using some failure recovery behavior. So here you can see some kind of a spiraling movement to actually get the plug into the socket, and also using a form of visual serving for the high precision tasks. The overall task is a kind of a longer sequence of steps, vaguely related to recycling electronic components. You have this box here with different electronic probes and buttons and latches and so forth. And then you need to do a long sequence of tasks. So here we not only have these failure recovery behaviors, but then also it's effectively, in this case, a very simple finite state machine that decides on the order in which to execute the subscales. And here's a little clip of the end of the sequence. Inserting that probe is actually one of the more challenging tasks, because you also have a ring around the hole. So if you put the tip of the probe into the ring, then you get stuck and you actually need to pull it out again and put it in and these kind of things. That's the part of wrapping the cable around we actually thought would be one of the more challenging parts. Turns out it's not that bad, as soon as we had kind of the human insight that sliding along the cable is a very good approach, so you can actually use the physical constraints of the environment to your advantage. And then, and you can move the box around, but obviously all the parts on the box itself are in a fixed location. So, to sum up, I today presented some of our work on teaching through interactions, which I hope I could convince you are one of the very promising ways of speeding up robot learning, because they really play to the complementary strengths and weaknesses of both the human teacher and the robot learner. I think these kind of methods are very promising, not only in isolation, and what I showed you today were very narrow tasks you could learn very efficiently, but there's many ways in which you combine them with other methods. So, I don't know, some examples might be to use a more generalist model that is based on a huge amount of data to provide you the initial movement, and then use these kind of ideas to fine-tune it, to really tailor it to the specific situation you have at hand very efficiently. The methods I showed you today, or the videos, they really were learning from scratch on the real robot, no simulations involved. But yeah, why not use simulations to very quickly get an initial policy? You could also use these kind of things to train the robot in simulation and then do the classical sim to real. You can combine them with reinforcement learning and so forth. And we actually wrote a massive, almost 200-page survey paper on that if you want to know more about the general area of interactive imitation learning. Like I was already alluding to in some of the videos I showed you, one of the big questions still is, how do humans like to teach? What I showed you today was still very focused on making the robot learning effective, and yes, we ran user studies, but then still how to make it intuitive for human teachers is still a big open question. And also there, the large language models and these kind of things will hopefully come in very handy. So for instance, enabling yet again a different modality of feedback by allowing vague spoken input for corrections or these kind of things. So to sum up, I showed you quite a few methods and ideas on how to speed up robot learning. So actually it was very much the humans helping the robot to get unstuck. However, obviously that's not our ultimate goal. Really, that's just kind of a means to an end in order to help robots, to help us and make our lives easier. So with that, thanks a lot for listening. That's a more or less recent picture of my group and some other collaborators and a few of the funding agencies that graciously supported the work. Thank you.
Thanks so much, Jens. Yeah, really nice talk. Nice to see lots of real-world robots doing lots of delicate and precise tasks. It's very nice to see. Do we have any questions? We have about 10 minutes or so. Anybody has anything?
Thank you for the interesting talk. And by the end, especially, we talked about basically uncertainty. And in one of the last projects, we were effectively detecting that uncertainty by modeling it with the Gaussian process. But in the work before that, I think, the one where the robot had put the cucumber in the bin,
Yep.
I might have missed it, but at some point, basically, it stops and effectively asks to be guided. How do you detect when it's uncertain, when the model is uncertain?
Shall I repeat the question for the recording, maybe?
Yeah, okay, that'd be great, actually. Thanks.
Okay, so the question was about how the uncertainty is modeled in different things I showed. In the very last one I showed you with the little card catching thing, there was actually a neural network that was used to model the different forms of uncertainty. For some of the other things, it's indeed a Gaussian process. And then your specific question was about the work where it's putting the cucumber in the crate. And there, it's indeed also modeling the uncertainty, which is very roughly speaking based on, we roll out the trajectory relative to the different reference frames, and we see if there's a big disagreement between them. And then based on that, you say, okay, it's too uncertain, they are too far away, and then it triggers the question to the user.
Yeah, thank you very much.
What was the name of the last paper that you showed where you take the cable and wrap it around?
So this one, you mean?
That one, yes.
So it's not really a paper. We have a very old version thereof is kind of a tech report that is on archive. However, if you Google that name, I can also give you the website. They actually provide all the source code and some documentation and some explanations on their website. So it's a mix of using vision in different forms. So how it effectively works is it does a rough visual calibration based on the location of the box, so you know how it's transformed, and then as much as possible, actually the movements are purely kinematic and not taking visual feedback into account. And if it's not very precise, then having the rough calibration relative to how the box moved is good enough. And for more fine-grained, precise tasks like inserting the probe, you need the visual feedback additionally. So it's kind of a visual feedback on an as-needed basis.
I was wondering if you could talk a bit more about
Yeah, so I guess like almost everybody, we've started playing with language models. Some of the things we've been working on is replacing this very simple whatever finite state machine we have in this one here with kind of using an LLM to figure out the sequence in which you need to employ these primitives. And then we've recently indeed started looking into how to use language feedback for corrections, but that's still in progress.
Yes, you mentioned you tried using inverse reinforcement learning to adjust the feedback in first parts. So what was the problem? Why did this idea go forward?
Let me see. I think I have the video somewhere in my backup slides. Come on, slow thing. No. Why isn't it working? No. Here. Stop playing? Yes. So here what we try to do is teaching the robot to move this kind of red point to the target. You're going to see in a second how it looks like. So it's actually a camera attached to the robot arm. Come on, let me try to scroll forward a little bit. No, wait. I thought it's in there. Okay. So here it's first based on a screen. So the camera has this this cross, and it tries to move it to a target. And in the end, what we wanted to do is to have it track the red ball. So here we're indeed teaching at the same time that having the red thing at the center is the reward function we want to optimize for, and how to do that. But then we ran into the typical problem of inverse reinforcement learning, that it's not unique and it gets stuck in some kind of local optima if you try to do them at the same time.
Yeah, question back.
In the example where you erase the whiteboard,
Yep.
there was a vector field close. I think I missed what that meant.
Yeah, so the question was about the vector field. Come on, here. So what that means. So effectively, the trajectory is represented as a Gaussian process, which tells you the direction in which it moves, so effectively the velocity based on the current state, then what's the velocity or the step you're supposed to take, and then how this vector field appears is that you have effectively data where you have initially the red dots, and then later on where you have the black line. And how we use the uncertainty of the Gaussian process, which tells you if you have data for a certain state effectively or not, is that, so if you don't have data, it assumes it's very uncertain. And then we follow the gradient of the uncertainty, which effectively means that here you're more uncertain, and then where you have data, you're very certain. So we follow the gradient of the uncertainty to pull it back to the area where we have demonstrations. And that's what those little arrows indicate.
Would you be interested in seeing whether there are bifurcations of such a vector field? It looks like you've got a cycle in tracking.
Yeah, so indeed bifurcations are a very interesting problem. Depends a bit on what you want to do. So like if you want to do a figure 8 and if you represent the state as including the velocity, then you don't have an ambiguity and that works nicely. If you really have an example where you approach an obstacle and you can go left or right around it, then in this case it won't work, and you would need to come up with a way probably to figure out, so to explicitly know that there are two different modes which you can follow. Otherwise, if you just average at a point where it's splitting, then it's going straight in. Yeah. We've done some stuff on that, where we actually figure out that there is this kind of ambiguity, and then what a master student back then did was just pick one of them, but explicitly be aware of it, and then request feedback for that. Yeah.
Yes.
Do you notice an increase in the time a human spends by like giving interactive demos like these, as opposed to collecting data for different combinations?
So, so the question is about the time it takes if you compare interactive demonstrations versus collecting a set of demonstrations initially. It's a bit hard to measure and fairly compare. So what, at least in our experience, happens quite often is that it's not a one-time thing that you collect a number of demonstrations. You start out with that, you have a set of demonstrations, you train the policy or the behavior of the robot, you test it out on the robots, and then if you're lucky it works, but more often than not you figure out, okay, I forgot this kind of scenario, and you start collecting additional demonstrations for what you forgot, and you get this kind of a more or less interactive loop already. While if you do it interactively, it's very natural to provide more data when it's really needed, when you see it's going wrong. We've ran a user study where we tried to compare that, and we're currently writing that up. And in terms of really the wall clock time it takes, interactive stuff was a bit quicker, but then in terms of what people prefer, there you can actually see a stronger difference.